In this video, I want to talk about incorporating interactions between our predictor variables when at least one of those predictor variables is categorical, like color, marital status, state of origin. And we've seen that in business analytics very often we do want to have categorical predictors in our regression models. If we're working for the development office at the University of Tennessee, we might want to use someone's major as a predictor. Are they accounting, business analytics, finance, or supply chain? If we're in retail analytics, we might want to use someone's marital status to help predict the amount of money people are spending at the store. So are they married versus single? And to do this, what we did was to represent each level of a categorical variable with an indicator variable, a 1 or a 0. If we were going to represent marital status, we have married and single as our two levels, and so we needed to create one indicator variable to represent that status. And the convention was whichever level came first alphabetically, we called our reference level, and that was represented by a 0, the other level getting to be represented by a 1. So with marital status, what we would do is we would assign the married people the number 0, the single people the number 1, and we could use that indicator variable as a predictor in our regression. If we were predicting donation amounts based on major, well, we have 4 levels in this case, so we would need a set of 3 indicator variables. By convention, the one that comes first alphabetically, accounting, would have zeros for all 3 indicator variables, and the other 3 levels would have an indicator variable named after it. So we'd have an indicator variable for business analytics. We'd have another variable for finance. We'd have another variable for supply chain. They would equal 1 if that was that major and 0 otherwise. And being able to incorporate these categorical predictors really helped us out for some key quantities that we needed to study. So one example of this was to look at the salary data set where we tried to predict this monthly salary of an individual at a company based on their education, their experience, the number of months they've worked for at this company, and then also their gender. Because we were interested in knowing if there was any systematic difference in the way that men and women were being paid at this company. So what we could do is we could fit a model that predicts salary from, for instance, education and gender. And when we do this, we could visualize what ended up happening. And in effect, whenever we incorporated a categorical predictor, the regression fit a separate line for each level of that categorical variable. So we get one line relating salary to education for men and another line representing salary versus education for women. And when we just have the categorical predictor in the model, what we have is a constant offset between those two lines. Those two lines are parallel, meaning they would have the same slope. The coefficient of education would be the same for both of them, but they're going to have different intercepts. And that separation between the lines represented the difference in the average salary between men and women after we accounted for other predictors in the model. So for instance, if we were to compare men and women that had 4 years of education, we would find that the coefficient of gender male, which is about $461, would be the expected difference in the monthly salary between men and women who had 4 years of education, or any other identical value of education for that matter. Now, we used this model to determine if there was any sort of systematic discrimination against women at this company, because we were able to fit a model that helped to predict the salary at the company based on the number of years of education, the number of years of experience, and the number of months working at the company. And when we did that, we could go and check out the coefficient of gender in our predictive model to determine what the average difference in salaries was between men and women after accounting for any possible differences in their educational experience levels or the number of months working at the company. So when we looked at the coefficient of the indicator variable representing gender, R represents it as gender male, we found that the coefficient was 450 and highly statistically significant. And this is why Harris Bank, the source of this data, ended up losing that lawsuit. So where else in business analytics might we want to incorporate categorical predictors into our model? Well, we could load up the Bulldozer data set. So we are interested in predicting the sale price of a bulldozer at auction based on, let's say, the tire size of that bulldozer, and then also the decade in which it was constructed. So if we throw the decade into the model, there's 4 possible values: the 60s and 70s one level, the 80s, the 90s, and the 2000s. So we're representing decade by a set of 3 indicator variables. And when we visualize that model, each different decade gets its own implicit regression line. They have the same slope, so the coefficient of tire in this case would be the same for all 4 of those decades, the coefficient being 2302. And what we have is a set of indicator variables with coefficients that tell us something overly specific that we're probably not the most interested in, because when we do have a set of indicator variables representing a categorical variable, those coefficients was comparing the average value of y for that level to the average for the reference level. So if we look at the output of summary for our Bulldozer model, we find that the coefficient of decade 1980s is 6269, letting us know that the difference in the average selling price between Bulldozers made in the 80s and Bulldozers made in the 60s or 70s was $6,269. Typically not the most important question that we have on our mind. Usually we'd like to know if there's any statistically significant difference in the average selling price across all the decades once we account for tire size. And that's where we were able to use that drop one function that was the partial f-test determining if we could drop the set of indicator variables representing our categorical variable. So in this case, decade is statistically significant in this model predicting the selling price of a bulldozer from tire and decade. Another place we might want to incorporate a categorical predictor would be predicting the demand for bicycles at rental kiosks based on the effective average temperature that was outside that day. So we could set up our model predicting demand from that temperature and the day of the week potentially, maybe it varies over the course of the week, and visualize that model. By incorporating that categorical variable, we have 6 indicator variables. The reference level Friday doesn't get one, but the other days of the week do. And when we go and look at the regression lines, one for each day of the week, they're going to have the same slope, but they're allowed to have slightly different intercepts, which represents the difference in averages across those different days of the week. Now, in this case, we see that these lines are very close to one another. There's very little separation in those lines, indicating that there's a pretty small difference in the average demands across the days of the week. So we might wonder, do we even need to incorporate day as a predictor? So we could run that drop one to determine, is the day a statistically significant predictor of the demand? So is there any difference in the average value of demand across the days of the week after accounting for temperature? And the p-value of the drop one, this partial f-test, comes back at 0.59. Since that's bigger than 0.05, we know that there's no statistically significant differences in the demand across the days of the week after we account for the temperature of that day. So the net effect of adding in a categorical variable as a predictor is to give each level its own regression line. They're all going to have the same slopes, but they're going to have different intercepts. And the difference in the intercepts was going to be the difference in the average value of y across the levels that we're seeing in our data. And if we look at those coefficients of the indicator variables, that was always letting us know the difference in average for that level versus the average for the reference level, whichever one came first alphabetically. Now, let's look at an example where just incorporating the categorical variable as a predictor isn't quite good enough, doesn't quite incorporate reality to the fullest extent. And for this, what I'd like to do is I'd like to load up a movies data set and examine the relationship between the rating on the IMDb webpage and the runtime of a movie. So let's load up a movies data set where we can study the relationship between a movie's IMDb rating and its runtime. And this is important because in this day and age, movie studios are more and more reliant on making money during its theatrical release. They're relying on people showing up to the theater and spending money because there's no such thing as video rental stores. Most of everything is just streaming these days. So what is the relationship between the IMDb rating and a movie's runtime? If we make a scatter plot, fit a simple linear regression model, and add that to the scatter plot, we see that there's a positive relationship. Looking at the coefficient of runtime in the movie, we see it's just at about 0.02. So that lets us know that when we compare two movies that differ in runtime by 1 minute, we expect the IMDb ratings to be different by about 0.02. It's positive, so the movie with the higher runtime is expected to have the higher IMDb rating. So we might wonder, okay, well, there could be more to an IMDb rating than just the runtime. What if we incorporated something about the MPAA rating? And specifically, let's examine whether a movie is rated G or not G. So if we go and look at a summary of our data, we find 63 G-rated movies in our data set, and the remaining being non-G movies. So here we have a categorical variable with two different levels. Is it a G-rated movie? Is it not a G-rated movie? No is going to be the reference level. We're going to assign that the value 0 for our indicator variable. Yes is going to be assigned the value 1 for our indicator variable. And when we visualize this model, we find that the two lines are pretty well separated. And in fact, what we see is that the line for G-rated movies is noticeably above the line for non-G-rated movies. And if we look at a summary, the coefficient of our indicator variable is about 0.69. Nice. So what we could say is that when we compare movies that have identical run times, the movie that's G-rated is expected to have an IMDb rating of about 0.69 higher than the equivalent non-G-rated movie. But we have to think about, is that really the way the real world works here? If we take a G movie and just, pad its runtime, make it a bit longer, is that necessarily going to be associated with a higher rating? Well, let's think about this. Let's actually take a look at a subset of those long movies that are G-rated, and we can see that it's a bit hit and miss. Some of these longer G-rated movies, like Ratatouille and Cars, receive very favorable reviews on IMDb, a high rating, but other long G-rated movies, like High School Musical 3, Senior Year, The Princess Diaries 2, not receiving as high an IMDb rating. And if we think about it, well, a lot of G movies are related or released for kids, and kids don't really have the longest attention spans ever, and it might be kind of a miserable experience to sit down a young kid in a theater for, a 2-hour movie. Maybe it's really the case that for G-rated movies, this relationship looks a little bit different. So if we look at the relationship between the IMDb rating and runtime for G-rated movies, we actually see that the relationship looks negative. There's a slight downward negative trend as we look at movies with longer runtimes. Those movies tend to actually have smaller IMDb ratings, and that kind of makes sense. If it's a movie that's going to be targeted for kids, you want to have that runtime be a little bit shorter. Otherwise, they're going to get a little bit antsy, a little bit impatient. They're going to lose their attention span, and too long of a movie, and the parents are going to be like, this was poorly designed. My kid started misbehaving. I just didn't like the movie here. So what we've discovered is that this pattern here, longer runtimes being associated with higher IMDb ratings, isn't necessarily going to be true for all MPAA ratings. Now, how are we going to make it so that G-rated movies have a different slope than non-G-rated movies? Because when we just add in G as a predictor of the movie's IMDb rating, that just gives a constant offset, either above or below the average rating for non-G movies. And the solution here is going to add an interaction between our numeric predictor, the runtime of a movie, and our categorical predictor, whether a movie is G or not. And by adding in an interaction, something magical happens. When we do have an interaction between a numeric predictor and a categorical predictor, each level of that categorical variable gets its own regression line with a different slope and a different intercept here. So how do we fit this model with an interaction? The same way we did when we wanted an interaction between two numeric predictors. We simply separate those two predictors with the multiplication sign. And when we do this and when we run visualize model, what we find is that, okay, by adding in that interaction, we're now allowing G-rated movies to have a very different looking regression line than non-G-rated movies. The G-rated movies have the negative relationship, and the non-G-rated movies have that positive relationship here. If we go and look at a summary of the model, what we find is that interaction is statistically significant. The p-value is less than 0.05. So we get a significant improvement in our model's ability to predict if we do include that interaction, and we do allow the line for G-rated movies to look different than the line for non-G-rated movies. And so we should probably ask ourselves, okay, well, what does the coefficient of the interaction term actually mean? So let's see how this works. Let's actually write out the entirety of the equation that the summary of the model provided. We have that rating is 4.39 plus 0.02 times runtime plus 3.56 times our indicator variable for if a movie is or is not G-rated minus 0.03 times runtime times our indicator variable. So let's recover the implicit regression equation. Let's go and find the regression equation when our indicator variable equals 0, in other words, for non-G-rated movies. Well, plugging in 0 for G yes in this case, what we find is we get this glorious cancellation. Anything times 0 is 0, so the equation very quickly simplifies to just be rating is equal to 4.39 plus 0.02 times runtime. All right, well, what about the regression equation for G-rated movies? If it's a G-rated movie, then our indicator variable is equal to 1, so we can go and plug in 1 whenever we see G yes in our regression equation. And so when we do this, what we find is that we have two terms that can be added together to give the new intercept for G-rated movies, and we have another two terms that can be added together to give us the slope of the regression equation for the G-rated movies. And so we see that the coefficient of the indicator variable that is not involved in the interaction lets us know what the difference in the intercepts are between that level and the reference. So here we have that the coefficient of our indicator variable for being a G-rated movie, 3.56, it's letting us know that the intercept is 3.56 higher than the intercept for non-G-rated movies, and so the new intercept becomes 7.95. The coefficient of the interaction term, that's going to let us know the difference in slopes for the regression line for our level of interest versus the reference level here. So the coefficient of our interaction term is minus 0.03. When we group together those two terms that had runtime in them, we're adjusting the slope from 0.02, which was the slope for the non-G-rated movies, our reference level. We're adjusting it downward by 0.03. We're subtracting 0.03 off of it. And what we end up with is a slope that's overall negative. The slope of the regression line for G-rated movies becomes minus 0.01. Among G-rated movies, two movies that differ in runtime by a minute are expected to differ in IMDb ratings by 0.01, and now, more realistically, the movie with the longer runtime expected to have the lower IMDb rating. So this is great. From a visual perspective, when we do add in that interaction term, that's just allowing our model to give each level of the categorical variable a different intercept, different slope, so that each level essentially gets its own regression line. And when we look at the output of the summary, the coefficient of the indicator variable tells us the difference in intercepts between that level and the reference, and the coefficients of the interaction variables lets us know the difference in slopes between that level and the reference level. One more example with movies. Let's try to predict the IMDb rating based on runtime, and then also whether or not a movie is comedy or not. So if we predict IMDb rating from runtime and our indicator variable for comedy, once again, they're going to have the same slopes, just different intercepts. And the vertical separation, that difference in intercepts, lets us know the difference in average rating when we compare movies of the same runtime, when one's comedy and one is not. And if we go and look at the coefficient of our indicator variable, we get minus 0.13. It is statistically significant because that p-value is less than 0.05, so it's letting us know that when we compare two movies with the same runtime, the comedy movie is actually expected to have a lower IMDb rating by about 0.13 compared to non-comedy movies. Now, should we allow for the possibility that the slopes of these lines might be different between comedy and non-comedy movies? Well, let's fit the model with the interaction here. Runtime times comedy. And from the visual perspective, looking at the two different lines, it does look like those lines have pretty different slopes. The slope for comedy movies looks to be noticeably steeper than the slope for non-comedy movies. Is the difference in slope statistically significant? Well, we can look at the p-value of the interaction term. And we find that while the interaction term is small, about 0.015, it is statistically significant because that p-value is less than 0.05. So in this case, it actually makes sense, just like for G-rated movies, to have two different lines relating the IMDb rating to the runtime for comedy movies versus non-comedy movies. So how does this analysis work if our categorical predictor has more than just two levels? And for that, let's look at an example where we're trying to predict the IMDb rating based on the full MPAA rating information. So we have G-rated movies, PG, PG-13, R, and also in other category. This might be unrated, NC-17, X, etc. And so in this case, we have 5 different levels. We're going to need 4 different indicator variables to represent them. By convention, the level that comes first alphabetically, G in this case, will not have an indicator variable named after it, but the others will. So we'll have an indicator variable named R, which will be equal to 1 if it's an R-rated movie, and 0 otherwise. We'll have an indicator variable named PG, which is going to be equal to 1 if it's a PG-rated movie, 0 otherwise, so on and so forth. So let's go ahead and fit that model, predicting the IMDb rating from the movie's runtime and the MPAA rating. And when we visualize it, if we haven't incorporated an interaction, we know that those regression lines, one for each level, are going to be parallel to one another. Same slopes, but different intercepts. And the difference in intercepts between those lines is going to be a comment on how the average IMDb rating differs from one MPAA rating to the other. So if we go and look at the summary of the model, the coefficients of those indicator variables are letting us know the difference in the average IMDb rating when we compare movies with that MPAA rating and the one with the reference level, in other words, G-rated movies. So let's interpret the coefficient of our PG-13 indicator variable, which we see is about minus 0.91. So if we compare two movies, one is PG-13 and one is G, and they have the exact same runtime, this coefficient is letting us know that we expect the PG-13 movie to have an IMDb rating that's about 0.91 lower than the G-rated movie. Looking at the p-value of that indicator variable, we do see that it is statistically significant. It's less than 0.05. So we can say that there's a statistically significant difference in the average IMDb ratings when we compare movies of the same runtime, and one is PG-13 and one is G. Now, is that a very interesting question? Well, not really. We'd like to test for the significance of MPAA rating as a whole. And so for that, we can run drop one to see if we can drop all of the indicator variables representing MPAA rating simultaneously. Now, the p-value of this partial f-test comes back much less than 0.05, so we can't drop MPAA rating from our model, indicating that there are some statistically significant differences in the average IMDb rating across our 5 levels of MPAA rating. Now, unfortunately, this test doesn't tell us where those statistically significant differences are. For that, you're going to have to take another business analytics class, either BAS 471 or BAS 479. You'll learn how to do that. But for now, we've discovered that when we do compare movies of the same runtime, there is a statistically significant difference in the average IMDb rating based on MPAA rating. Not all ratings are created the same. Now, it might be more realistic to actually give each MPAA rating its own regression line, not only different intercepts, but also different slopes. So let's see what those look like by fitting in an interaction with that model. So when we fit the interaction and visualize it, we do find that the 5 different MPAA ratings look to have pretty noticeably different slopes. We've seen this before. The G-rated movies actually have a negative relationship between the IMDb rating and the runtime of the movie. The other 4 MPAA ratings have positive slopes, and it looks like R has the largest slope of all. So let's look at the coefficients of these interaction terms and see what we can learn about them. So first, let's hone in on the coefficient of the interaction term runtime versus the R-rated movie here. So we see an interaction term of 0.032. We find that it's statistically significant, but what is that telling us? Well, it's telling us something really, really specific. It's letting us know that there is a statistically significant difference in the slope between R-rated movies and our reference level, which was G-rated movies. So R-rated movies, G-rated movies, different slopes. Yeah, we kind of already knew that. And
that's oddly specific.
Normally, we'd like to know, is there any difference in slopes across the 5 levels we're considering? And for that, we really need the partial f-test. We need to run this through drop 1 so we can see if we can drop all 4 different interaction terms simultaneously. Now, the p-value of the partial f-test comes back 0.002, less than 0.05, so as a whole, those interaction terms are statistically significant. We need to include them in our model. It doesn't tell us which slopes have statistically significant differences from each other, but it does let us know that not all 5 are created the same. So we saw with the coefficient of the R-rated interaction that the slope for the R-rated movies was 0.032 higher than the slope for the reference level for G-rated movies. What if we wanted to compare the slopes between 2 other MPAA ratings? Well, to do that, what we're going to do is we're going to subtract the coefficients between the 2 levels that we're interested in comparing. So what's the difference in slopes between R-rated movies and PG-13 rated movies? Well, what we can do is we can subtract those 2 coefficients. The coefficient for rating R is 0.032, the coefficient for PG-13, 0.033, and when we subtract them, we actually get minus 0.001. So actually, the slope for those PG-13 movies, the highest of all of the different MPAA ratings, the slope's a little bit higher than the slope for the R-rated movies. So if we're interested in comparing two arbitrary level slopes, just subtract the two coefficients and it'll get you there. So why does this work? Well, let's math it out to see why adding an interaction term allows each one of these MPAA ratings to have a different slope and different intercept. So if we go and write out the entirety of our regression equation, it's a long equation. So ratings equal to 7.95 minus 0.01 times runtime minus a whole bunch of coefficients and indicator variables for just the MPAA rating by itself. And then we have a whole bunch of additional interaction terms multiplying runtime by the indicator variables for those MPAA ratings. So let's go and see what those regression lines look like for movies of different MPAA ratings. For G-rated movies, that's our reference level. Every indicator variable gets a value of 0. So we got a lot of glorious cancellation going on between these terms because whenever we multiply 0 by anything, it becomes 0. The equation relating runtime to IMDb rating for G-rated movies is very easy to recover. 7.95 minus 0.01 times runtime, the original intercept of our regression equation and the original slope of the runtime predictor. Now, what about for R-rated movies? What we can do is we can go plug in 1 whenever we have our indicator variable for R and 0 for the other indicator variables. So doing that, we have a lot of terms that just become 0 because 0 multiplied by anything is still 0. And then what we see is that the coefficient of the indicator variable for the R-rated variable is adjusting the intercept. And what the term is for the interaction variable, the coefficient, that's going to be what's adjusting the slope relative to our reference level for G-rated movies. So when we combine our two terms that contribute to the intercept, the 7.95 and the 3.53, subtract them, we get the new intercept for our R-rated movies. And when we combine those coefficients multiplied by runtime, we find that the coefficient of runtime for R-rated movies works out to be 0.02. So R-rated movies getting an intercept of 4.42, slope of 0.02, and we can see that those coefficients of the indicator variables and the interaction terms are just adjusting the intercepts and adjusting the slopes. Now, as a final example, let's load up the CUS loyalty dataset from Reg class. What I'd like to do is I'd like to study the relationship between the lifetime value of a customer, the total amount of money that customer has spent with that company, and their income bracket. Are they between 0 and 30,000 per year, 30 to 45,000 per year, et cetera, and also the wallet share of that customer. So the wallet share is simply the percentage of purchases that the customer makes at that company versus the competitors for similar products here. So for example, if you spent 30% of your money at Kroger when you're doing grocery shopping versus 70% at Food City, well, your wallet share for Kroger would be 30, your wallet share for Food City would be 70. And we could expect that there would be a nice tight relationship between these quantities. So if we ran the associate command to see is there any statistically significant difference in the lifetime values depending on income bracket, we find that there definitely is. The p-value comparing the averages to each other is much less than 0.05, and we can see that almost uniformly as we go from one income bracket to the next, higher and higher incomes, that average lifetime value tends to increase. Kind of makes sense. And then also, if we look at the relationship between the customer's lifetime value and their wallet share, we find a fairly strong positive relationship. Customers with larger wallet shares tend to have higher lifetime values as well. Makes sense. So let's incorporate information from both of these predictors, wallet share and income bracket, when studying the lifetime value of a customer. If we predict from both of these quantities with no interaction, what we get are separate lines for each income bracket. They're going to have the same slope because there's no interaction, but they're allowed to have different intercepts. The difference in intercepts, those vertical offsets, are letting us know the difference in average lifetime value when we compare households with the same wallet share, but different income brackets. And if we were to go and look at the result of drop 1 to see could we drop all of those indicator variables, is there any statistically significant difference in lifetime values based on income bracket once we account for wallet share, we actually find that the p-value of the partial f-test is 0.42. That's bigger than 0.05, so it's letting us know that the set of indicator variables representing income bracket is not statistically significant. Once we know a customer's wallet share, we don't need to know anything about their income bracket in order to gain insight about their lifetime value. But maybe this is an overly simplistic view of the relationship between customer lifetime value and wallet share. What if we let each income bracket have not only different intercepts, but then also different slopes? Because the strength of the relationship between customer lifetime value and wallet share might vary depending on our income bracket. So refitting that model, now allowing the wallet share and the income bracket to interact, we find that when visualizing it, we do find noticeably different slopes for our 6 different income brackets. And in fact, we gain quite a bit of insight because the variation looks pronounced enough that we can learn something about how to interact with different households. Running the drop one test, we actually find that the interaction variables are indeed statistically significant, the p-value much less than 0.05. So it does look like the 6 different income brackets don't quite have the exact same slope. So what are the implications? Well, visually, what we find is that the slope for the highest income bracket, the 90,000 and above, is the highest, whereas the slope for the lowest income bracket, the 0 to 30,000, is the lowest. Now, that's not the most interesting observation by itself, but notice at what the regression model is letting us kind of glimpse for very low wallet share versus very high wallet share customers. If we look at customers with very low wallet shares, customers that spend most of their money on these sorts of purchases with their competitors, what we find actually is that the highest income bracket has the smallest lifetime value. The 90,000 and above here, their line is below the rest of the lines. Now this switches though, if now all of a sudden we look at customers with high wallet shares that are spending most of their money on similar purchases at this company versus their competitors. Now the line for the highest income bracket, 90,000 and above, is by far above and beyond what the lines are for those other income brackets. So what have we discovered here? Well, actually, we've unearthed some pretty actionable insight. So in our first analysis with Associate, we found that the higher the income bracket, the higher the lifetime value. So the marketing team, the customer retention team, the customer interaction team might say, oh, well, let's make sure to focus in on the highest value customers, those that have very, very high income brackets. But we're learning actually that the story is not so simple because the value of a high income bracket customer actually depends a bit on what their wallet share was. If we focus in on customers with relatively low wallet shares, customers that are spending most of their money on similar purchases with competitors versus this company, we actually find that those higher income bracket customers are worth the least of all of the other income brackets because the line for those high income bracket customers was really far below at small wallet shares compared to where the lines were for the other income brackets. It's only when we started looking at those customers with high wallet shares that were spending most of their money for like purchases with this company versus their competitors that that high income bracket really shines. So there you have it, incorporating interactions between our variables when one of them is a categorical variable is an essential tool that you need to know to come up with reasonable reflection of realities in business analytics. By incorporating that interaction, we're going to allow each level of our categorical variable to not only have different intercepts, but then also different slopes to capture the possibility that the strength of the relationships might be different as we move from one level to another. There might be cases where we see a big difference in the average value of y between our levels, and other cases where we find a very small or negligible difference. And understanding the magnitude of those differences can be the keys to making correct decisions.